Thank you, Laura, for this invitation, and thanks everyone for attending this remote conference. For some of you, and for some of you, thanks for being in person. I hope to visit at some point when travel will permit. So my talk today will discuss some of the recent research I've been involved in into the calibration of forecast from stochastic approaches to neural networks for basically modeling data which are highly, high frequency sample data. They could be vectors or they could be spatially indexed. It really depends on the application. So this is research led by one of my PhD students, and it's supported by NASA. So I want to start by giving you a very brief motivation on why do we need data-driven approaches for environmental problems, which is kind of my main area of research. I'll talk about one particular data-driven approach, which I've been focusing most of my research effort, which are neural network in time, which are dynamic or recurrent neural networks. And in particular, I will talk about the issue of uncertainty. So how do we assess the uncertainty as a statistician with a model-based approach? What's the best way? What's the most efficient way to assess the uncertainty? I'll talk about how do we actually calibrate the uncertainty. So how do we make sure that the 95% confidence interval I mean any interval basically is reflective of the true variability in the data. I'll talk about an application to citizen science data, urban air pollution in San Francisco, and I'll also mention very briefly some of my recent work on forecasting quasi-oscillatory climate processes, and in particular, I'm referring to El Nino, which is like the #1 climate index. So for those of you who are interested, we have a manuscript which is in archive now. You can just Google Bonas and Castruccio 2021, and it's in there. So in terms of data-driven processes, why do we need data-driven processes in a field such as environmental statistics, where there are lots of equations than there is a physics? Now, if we aggregate data on annual level or monthly level, the data regularly well behaved. You can see here a map of the US US wind speed on the left, and you can typically model these things, especially on a small scale, with diffusion equations, especially temperature. You have diffusion equations, stochastic versions of diffusion equation, reaction diffusions, which have a geostatistic equivalent in the Matern covariance function and all their derivatives. So you can define models through stochastic partial differential equations, which are ultimately physical models, and they work pretty well the moment you have this kind of level of aggregation, annual or monthly. Now, the problem arises whenever I'm modeling something at very high frequency. So 5 minutes winds, for example. Here you can see a snapshot of global wind every 5 minutes. So when you do these things, all sorts of turbulence comes into play, all sorts of dependence of initial conditions. The physics is just not as effective as a forecasting tool as it was before when we were dealing with monthly or annual levels. So in those cases, we really need other models which are really not driven by the physics, but are driven by the data. And in particular, I am referring in this work to neural networks. Now, just to make sure I have everyone on the same page, let me just define a few things here. Y of t will be the focus of my presentation. It's a vector of data. This could be a multivariate vector or maybe a spatial vector. It doesn't really matter. And my goal is the standard textbook problem of forecasting at a certain time horizon. So I want to get the conditional distribution of y of t plus k given all the past history, y of t all the way to y1, using this approach, which I will define a dynamic neural network. Now, allow me to define first a neural network, because I will be needing this definition and the discussion of uncertainty for introducing the dynamic version. So allow me now to just drop the index y for a second, the index t for the subscript t for a second, and let's assume I'm on a static setting, and let me define what is a neural network. Now, it's a very complicated and long topic, so I'll just cover the bare basics here. So the simplest neural network that you can think of is one which is shallow, meaning it has only one layer, and it's Gaussian. So it has basically continuous data, and it has a Gaussian error. So from a statistician, from my point of view, this is just another model, which is a generalization of a linear model. And you can write down your shallow neural network with this expression over here. It's kind of like a linear regression where you have yx beta plus epsilon, except now you have this gxw times beta. Now, the hard part here is basically that W is a matrix of unknown parameters, and there are many of them, P times D. Beta is not that complicated. It's just your standard linear vector here. It's not that long, and you can estimate it with your favorite penalized method. And really, the secret sauce of a neural network, what makes the neural network flexible is this function G, which is a nonlinear function, and there are many choices of these nonlinear functions out there. I'm not going to cover it. The point is that this is the standard, classical, simplest possible neural network that you can think of. And if you were to perform inference on this neural network, it's hard, but it's possible to do it. There are methods in machine learning called backpropagation algorithms to compute closed forms for the derivative, for the gradient. And so we can compute the optimum of W in a relatively fast manner. The problem, as a statistician, the question that I ask myself is, what about the uncertainty? So how can I estimate the uncertainty of the parameters W, all the entries of this matrix W? And there are approaches that have been around for about 10 years, Bayesian neural networks, which basically allow to perform some approximate Bayesian inference with variational-based methods. Now, the problem with these approaches, coming back to my problem of time series, is that I need something fast. I cannot do variational based because it's too slow. If I'm sampling data every 5 minutes or every 10 minutes, I cannot have a point estimate and an uncertainty which takes 30 minutes to forecast. So I need something much faster than variational based in order to have some sensible definition of uncertainty here. So for times, so the main idea to kind of improve things, to make things faster, is basically two. So the first one is, instead of assuming that W is this gigantic matrix of unknown entries, you project this W into a stochastic low-dimensional space. So you assume that W is a realization from a random matrix, and it's coming from some parameters, theta, which are controlling the distribution of W, and theta is low-dimensional, typically 2 or 3 or 5 dimensions. The benefits are obvious. If this is a random matrix, I can assume this to be a sparse matrix as well. So I have lots of zeros in the W's. So I can do sparse linear algebra. And on top of that, since theta is now low dimensional, I have a manageable posterior sampling. I kind of sidestep the curse of dimensionality, and I can take samples in a relatively fast manner. So this idea here, it's not really necessary to be applied for shallow neural networks, but the moment I talk about data in time, then things become a bit more complicated. So remember, my focus is to do the forecast on data which are, with high sampling rate in time. So the equivalent of a standard neural network in time, there are many possibilities, but the classical one that I will be focusing on here is something called a long short-term memory process, okay? And again, if you're coming from statistics, this is basically state space model with long range dependence. So you have your observations here, Y, your H is the hidden state, and the hidden state has a linear combination of the past state plus some W, which accounts for the long range dependence, and sorry, not W, omega. And omega t is a transformation of, again, the past state plus the contribution x of t of the input in your data, okay? Now, this is, again, a standard, very simple neural network in time. This is a long short-term memory process. I have a lot of parameters, but in fact, most of them can be estimated in a relatively straightforward manner. Beta, for example, here it's easy. You can just use penalized regression. There are only 3 parameters that you can find here: alpha, mu, and sigma square, which need to be estimated. The real issue is those parameters, is those matrices W and WX. So how do I estimate these matrices here? Remember, I need to do these things in real time, so they need to be fast, these things. So I will be applying this idea that I just mentioned before. So instead of assuming that I have just entries to estimate, I project everything into a low dimensional space, and I assume that I have, using Bayesian terminology, a spike and slab prior. meaning that every entry of W and WX can be 0 with a certain probability. And if it's not 0, it's coming from a symmetric distribution, which could be uniform, or it could be a Gaussian distribution, or a T distribution, you name it, as long as it's symmetric. Okay? So these models here have been around in machine learning literature. They are called issue state networks. And if you want to have a kind of pictorial representation of how they look like, you have your past history, y of t minus 1. These are your data. They get into these random metrics. And for every realization of W, I have a different matrix. I multiply this with some linear algebra operation through this linear filter beta. And then I have my forecast y of t plus 1, y of t plus 2, all the way to y of t plus k. So for every realization of W, I have a different forecast. Okay? This means that I can predict things, I can make predictions using the classical ensemble-based approaches. If every realization provides a forecast, I can do multiple forecasts, and I can use the kind of cloud of forecast, the uncertainty generated by the forecasts, as my reflection of the uncertainty in the data. So if you do this and you were to produce, say, a one step ahead forecast, you end up with things like that. The red line is the true data, the black line is the prediction, and this functional box plot represents basically the uncertainty. Now, this is where my research starts. Then you look at this and you say, well, is this really a good uncertainty? Is this really a reflective of the true uncertainty in the data? If I generate a 95% confidence interval, do I have 95% of the data covering this? Is this a calibrated forecast or is it not? Now, in order to address this question, I want to calibrate my forecast. I need to have, remember, something fast because it needs to be done in real time. And I need something simple because, again, the computer has to do these operations in a relatively efficient way. So the key idea of my approach is basically threefold. The first one, and this is really the simplest one, is to use a machine learning approach, a very kind of computer sciencey approach on the uncertainty here, which is the following. Now you have this uncertainty from the ensemble, you adjust this uncertainty using a training set. So the data that you have as a training set are also used not just to assess the point prediction, but also the uncertainty. And if the uncertainty is over or underestimated, I will adjust the uncertainty using the training set. And with the hope that the uncertainty in the training set is going to be more or less the same that the uncertainty in the future. Second idea, calibrate marginally. First, focus on every element in your matrix or every point, every location in space, and do the calibration. And the third idea is that once you're done with the marginal calibration, you can come up with a relatively simple spatial model to do the multivariate or the spatial calibration of the problem. Now, I'm not going to show you the equations. They're too long for this talk. I don't have time for that. I'm just going to show you the picture that gives you the idea. So remember, I'm in the training set, so I know everything. I produce a prediction for y of t plus 1. So this is my y hat of t plus 1. Not one prediction, but many predictions. Because remember, those matrices W are random. So for every realization, I have a different ensemble member. I generate my histogram, and I compare this histogram with the true value y of t plus 1, because I am in a training set. And I do the same for y of t plus 1 all the way to y of t plus k. Now, once I've done this, I have the true value, I have my uncertainty, so I can adjust. You take your forecast, you take your true observation, and you can compute the sample standard deviation, which is now reflective of the uncertainty around my prediction. And I do this for every step. This is going to be the uncertainty at step 1, step 2, step 3, step k. And I know that as I move further ahead in time, my forecast has to be more uncertain. Of course, because predictions in 5 years are going to be much more challenging than predictions in 1 year. So how do I account for that? Well, in the next stage, you smooth the sigma hat square k with a monotonic spline. So you plot them, you do the smoothing, and then with this estimated variance, you do the marginal calibration under the assumption of Gaussianity, which is, remember, one of the key assumptions that we made at the beginning of the model. Finally, once we have all of this, we fit a spatial model because we have calibrated things marginally. Here, again, I'm not going to explain the model. It's a relatively simple non-stationary spatial model, which is convolution-based using a few knots in the domain. So this is the approach. I have applied this model to citizen science data in San Francisco during the wildfire season. And the goal is basically to understand exposure to hazardous air pollution. What you can see here is a plot of where those networks, those monitoring stations are. Those are privately owned. Those are owned by citizens in San Francisco. They're coming from a network which is of relatively cheap data. They're about $150 per station. So really anyone can buy this, and then they upload the results over the internet. The star here represents the only like federal funded station for which we have calibrated our data here. So now we apply our model here during the fire season in San Francisco, and long story short, it works. So what you can see here is this is your true value, the solid red line here. The solid black line here represents my prediction, and the dashed lines are my 95% prediction interval. You can see they're relatively smooth, and they are increasing in time as you would have expected. Now, this is not a proof, of course. This is just a plot to kind of qualitatively see that things behave the way they should. In terms of quantitative assessment of this method, you can compare issue state networks in terms of point prediction with other approaches. For example, our FEMA models, which are basically ARIMA models with a modification for long-range dependence. You can compare them with state space models, with hidden Markov models. And the bottom line is that the mean squared error or continuously ranked probability score, choose your favorite prediction metric. They work, they are much better than these approaches here. And also they have a smaller uncertainty around all the locations in our application. Now, in terms of our proposed approach for calibration, the results are dramatically better. So if you think about not applying any type of calibration to this problem, you end up in a nominal 95% confidence interval with a coverage of approximately 37%. If you adjust, then you have 94%, basically 93.6%. And the uncertainty around the different stations is such that 95% is well within the interval here. Okay, so we have effectively calibrated the uncertainty marginally, but also if we take the average here, look at this, you go from 20 to 86% coverage on a nominal 95. 86 is not perfect, and the reason for that is that evaluating the uncertainty of the average across all stations is a very challenging problem, and all it takes is a tiny misspecification of the spatial component to have a different variance, a misspecified variance. So even a tiny misspecification is going to be big. So 86% is pretty good for the grand mean. And now with this approach, we can now predict exposure. So we can say we are at a certain day in San Francisco. You can make predictions on what's going to happen over the next 7 to 10 days. And you can cross-reference this data with population. And you can ask yourself the questions such as how many people will be exposed to a level of air pollution which is going to be above a safe threshold level. So what I'm showing you here is a prediction from, I think, 5/19, so May 19th to May 25th of 2021. And the areas which are above 12.1, which is a harmful threshold for vulnerable people, according to the WHO standards, this is going to be the area which is going to be mostly affected by it. Okay, so we have also applied this model to climate models, to large-scale applications such as El Nino. Again, just for the benefit of everyone, El Nino is basically this kind of quasi-oscillatory behavior that happens across the equatorial Pacific with two phases, warm and cold. And when it's warm, it creates all sorts of issues in equatorial Asia because there are lots of wildfires. When it's wet, when it's La Nina, it creates all sorts of issues because it's more rainy, it's more wet, so there are lots of floods. So it's important to predict this phenomena, but as you can see here in this plot, it's not so simple. It's not really an oscillation, it's something more complicated. So in another work that we have recently submitted, we have actually worked on applying these methods to El Nino. And again, the bottom line, it works. Here you can see the actual values according to the climate simulations. Those are CMIP-60 simulations. So those are the ones that have been just uploaded from the IPCC assessment report. And this is the prediction. So you can pretty much see, at least visually, that things work the way they should. All right, so conclusion. So dynamic neural networks have been around for, I would say, more than 20 years by now in computer science. And I mean, I always find it surprising that they see that they're kind of different mindset on these problems. They really see these dynamic neural networks as a workaround for stability issues, backpropagation as stability issues. So instead of relying on them, you propose this kind of stochastic methods to have something more stable. And my contribution is really twofold here. The first one is to kind of have a more model-based, a statistical approach to neural network. For me, as a statistician, these neural networks are just another model. And so the fact that you have simplified numerical algorithms is just a consequence of the fact that you have avoided overfitting the data. Okay, so I'm not really aiming at smoothing the data by themselves. This is not the ultimate goal. The ultimate goal is to provide a model which assesses the uncertainty in a correct way. And on a more practical basis, I proposed an algorithm for calibration, the ensemble forecast. It's fast, it's simple, it quantifies the uncertainty correctly, and you can basically use it as a second step approach after the prediction has been proposed, so that your uncertainty is really the one that you would have expected from the data. So that's it, basically. Thanks very much for your attention.
Thank you, Stefano. Very nice and interesting talk. Then I will give the public the possibility to ask you questions or comments. Are there any questions or comments on this work by Stefano? If not, I want to know if your procedure is available to try to reproduce it in another data set, or you have the code for the whole thing, including the calibration.
So it really depends on the problem. In some problems which have long-range dependence, we have worked with El Nino, with the PDO, which is Pacific Decadal Oscillation. All these kind of oscillatory behaviors in the climate are ones for which this kind of approaches work pretty well, and we have evidence for that. So, Mark, do you have a question?
Yeah, I think so.
Yes, yes, Stefano, thanks. It was a very nice talk. I wonder about the application to San Francisco. Can you validate this region of exceedance? Because it seems very kind of smooth in some sense. So it's kind of the bottom part. And
this
so,
one here.
Yeah.
At the moment, I mean, the only way we could validate that is with hospitalization data. And these hospitalization data, they are really, really hard to get. Mm-hmm. So we have now some hospitalization data from Charlotte with another project. And I'm hoping through the same network at some point to have that. Because I agree, all we can do at the moment is validate these citizen science data. And you can see here, you have all these network here, and you have only one observation which is calibrated here. Yeah. So even calibrating just every single observation in air pollution is hard, let alone exposure. So exposure, I really don't have a way to say, well, you know, this makes sense or this doesn't make sense, unfortunately.
Okay.